Okay, so hello everybody. So I'm Professor Jackson, and I'm just going to say a few comments here about the applied EM concentration area. Here's some pretty pictures, first of all. Different devices, different things that relate to the area of applied EM. Maybe you can scan your eyes over those and just see how many of those you can recognize. So we have things like, power substations, big transformers and generators, microwave circuits like power splitters and hybrid 90-degree couplers and filters, and antennas like a microstrip antenna array, big phased array for defense purposes called PAWS, base station antennas. So a lot of different things there. So all this is the applied EM area. Okay, now in the applied EM area, let's talk a little bit about the courses here. Now 3317 is called Applied Electromagnetic Waves, and as it says, that's mandatory for all students, whether you're in the EM concentration area or not. Now, if you're in the EM concentration area, then you're required to take those three courses that you see below here: the microwave engineering course, the antenna engineering course, and then applied electricity and magnetism, 3318. All three are required. Now, I've divided these up into two different categories for convenience. One is called high frequency and one is called low frequency. They're very different. So the high frequency courses, microwave engineering and antenna engineering, as the word implies, deal with high frequency devices, high frequency concepts. So in other words, things going on at microwave frequencies, which is how we normally transmit signals from one point to another on a microstrip line or through space with an antenna and so on. Whereas 3318 is what I call low frequency. That's more relevant to things like power engineering. Power engineering is at 60 hertz or 50 hertz in Europe. And at those kind of frequencies, we think kind of differently. It's like a low frequency type of thinking versus high frequency thinking. So 3318 is really a course that's geared towards low frequency EM. You can call it statics if you want, which is zero frequency, but really it's low frequency in general. So very different types of sets of courses there. Okay, so again, in the applied EM concentration area, those three are the required courses. And of course, you have different courses you can choose from for your 7 concentration electives, including this one here. I'll say a couple more comments about it later, the Modern Optics and Photonics course, which is sort of an EM course, not exactly, but sort of. And also you have things like nanotechnology, introduction to telecom, electromechanical energy conversion. So things that are sort of related to power or things that sort of involve EM to some extent. There's courses on here that have nothing to do with EM, for example, DSP and analog electronics and so on. So it gives you some, diversity to choose from in your concentration electives. Okay, so let me say a few more comments about high frequency electromagnetics. So again, high frequency could relate to things like antennas. You see over here, right? Like base station antennas, microstrip antenna arrays that are high enough frequency where the whole array can fit in your hand. And also things like high frequency filters. So here, like from the microwave engineering course, here's a high frequency filter, some kind of like low fast, maybe like a Chebyshev filter, something that you can use to filter signals. So at high frequencies like microwaves, we don't design filters with just lumped Allen C's like you can get in your lab kit. Instead, we make inductors and capacitors out of things like microstrip lines, transmission lines. So this whole thing is actually a very compact way to make a microwave filter. And here's a microwave integrated circuit, which means various circuits are all integrated together into a compact printed circuit type of form there with input and output connectors. Low frequency, again, think like 60 hertz, think power engineering. So again, you might have substations, transformers, generators, distribution systems. So low frequency EM means things that are relevant to those type of areas. So again, in the high frequency EM, we have in the concentration area, the microwave engineering course and the antenna engineering course. So if you scan through this, you can see some of the, taken from the course catalog, some of the main topics that are taught in each of those courses. So in microwave engineering, you have passive components like transmission lines and waveguides, microstrip lines. We talk a lot about the theory of scattering parameters, scattering matrices or S matrices, because that's a very important thing for microwave engineers to really be aware of. You don't really meet that in the 3317 course, but in the microwave engineering course, this is a very important part of the course. And then things like impedance transformers and resonators and filters and so on. In the antenna engineering course, as the name implies, it's really pretty much focused on antennas. The whole course is antennas. And as you read through this list here, you can see different types of antennas and also techniques for analyzing and plotting their patterns, studying their behavior, and so on. But it's all focused on antennas. Both of them require 3317 as a prerequisite, because again, 3317 is sort of the undergraduate high frequency course. All right, so here's more details. So here's the microwave engineering course. And again, this microwave engineering, the way we teach it here, the course is focused on passive microwave engineering components. So that includes things like transmission lines, resonators, couplers, filters, and so on. And the theory that goes along with them, like, for example, the S matrix theory. Now, in this course, we don't really do anything with active components or active devices. Active devices would include things like oscillators, amplifiers, mixers, etc. But if you want to have exposure to active components, it's possible that you might think of taking this course here, 6353, which is called the RF and microelectronic class. Now, that's a graduate level course, not an undergraduate class, and it doesn't have an undergraduate counterpart. But as an undergraduate student, you can get permission to take a graduate course. So if you really want to take as much microwave engineering as possible, then beyond the 5317 class, you can take this one if you like to get exposure to the active components. Anyway, as it says here, microwave engineers work for a wide variety of companies. Many companies nowadays really, are trying to recruit microwave engineers. And if you take, microwave engineering as your concentration, and even better, get exposure to some of the graduate level microwave topics like the 6353 course, chances are you'll be in hot demand out in industry because microwave engineers are really in demand. Okay. And again, the microwave engineering course provides a good introduction to this area. The 6353 course provides even more exposure to this area. Now, I'll also make a plug for a 5113. That's called the microwave engineering lab course. Now, it's not an actual hands-on lab in the sense that it's not a measurement lab. Instead, it's a software lab where you get to learn how to use HFSS, which is probably the leading commercial software that's out there in the microwave industry for analyzing anything at high frequencies, including antennas and microwave circuits, etc. So it's a 1 credit hour lab class where you basically learn HFSS and how to use it to solve something practical like a filter or something like that. Okay, so it's optional. You don't have to take it. You take the microwave engineering course. But again, it's a very nice thing to think about if you want practical exposure to actual microwave software, like, in particular HFSS. It's a wonderful thing to have on your resume that you know HFSS if you're in the microwave area. Here are some pictures taken from microwave engineering. So again, the theory of scattering matrix parameters, kind of the bread and butter tool for microwave engineers, designing broadband impedance transformers, power dividers. This is like a two-way Wilkinson power divider, quadrature hybrids, for example, for getting circular polarization. So these are all what we call passive components, right? That's what we analyze in the microwave engineering class. And again, in the lab class, you learn HFSS, and here's like a typical antenna, a microstrip patch antenna shown being meshed up by HFSS. So it subdivides the space into a bunch of little tetrahedrons, and then it applies something called the finite element method to solve Maxwell's equations and analyze the structure. So you can analyze it, find like the S parameters, the input impedance, the radiation pattern, whatever you want to know about the antenna or the device that you're analyzing. So that's the kind of thing you're going to learn to do in the lab class, 850-113. Okay, so for 5318, that's the antenna engineering course. And again, it focuses pretty much just on antennas, so antenna analysis and design. As it says here, antennas are used a lot in wireless communications. I mean, that's what wireless communications is all about, right? You communicate with antennas. So it's very important for the wireless communication area. And it provides a good background for those that want to know more about antennas, or just those that want to learn more about wireless communications and other applications of antennas. For example, they're often used for sensors and other things. So sensors, communications, wireless communications, they all rely on antennas. And maybe the antenna engineering course gives you a little bit more than you need to know, but still, it's a really good course, and I strongly encourage you to consider taking it. Of course, it's required, though, if you're in the EM concentration area. Okay, here's some pictures taken from antenna engineering. So here's a typical what's called radiation pattern of an antenna, showing how it radiates in different directions. That's what antenna engineers are very interested in. Here's a typical type of antenna that we actually fabricated in our lab some years ago. Actually, with some undergraduate students that were working on a senior design project that did this. They were making a certain type of antenna called a microstrip antenna, but they made it in a transparent form, as you can see here. So the actual antenna is completely transparent. And that was nice because they wanted to put it on a CubeSat so the light from the sun could actually go through the antenna and reach the solar panels. So it's actually an interesting kind of transparent antenna. All right, let's talk a little bit about low frequency EM. So again, low frequency EM means things like 60 hertz or 50 hertz. So it's relevant largely for the power area. And we only have one course really that relates to low frequency, and that's the course 3318, which is again is normally an elective, but it's required if you're in the EM concentration area. And as you can see, if you read through this list, it is a good introduction to basic electricity and magnetism and vector calculus, Maxwell's equations, all the stuff that relates to circuit theory like Kirchhoff laws, but then electric and magnetic fields, inductance, capacitance, etc., magnetic fields, transformers, generators, motors, everything that relates to low frequency electricity and magnetism. Now, be aware of the fact that 3318 can be taken before or after at the same time as 3317. Because 3317 is mainly high frequency EM and 3318 is mainly low frequency EM, the two do not overlap that much. I mean, they both have Maxwell's equations in common, but really they're pretty much independent of each other. So you can take either one before or after the other one, or even at the same time. So as it says here, 3318, the low frequency EM course, is certainly very useful for power engineering. In fact, that's why it's required, by the way, if you're in the power engineering concentration area. It's also useful for nano engineering, nanomaterials. Why is that? Well, because in nano engineering, everything is really, really small at the nanoscale. But if your things are really, really small, your devices are really, really small, then really low frequency concepts are appropriate, because everything in EM is really what is your dimension compared to wavelength. If you're down at nanometer scales, of course, everything's going to be small compared to wavelength. So you can just use low frequency EM to analyze your devices. Okay. So that's why it's relevant for nano engineering in addition to power engineering. But, typical examples of things you can do, like in this course, would be calculating the fields from power lines, learning the basic principles so you can design motors and transformers. And if you're in a nano course, it'll help you to understand the nano and magnetic devices. So it gives you a good introduction to all of that kind of stuff. And I would argue that 3318 is also just a good foundation for every other EM course, because really 3318, probably more than any other course, gives you the most in-depth knowledge and understanding of Maxwell's equations, and also vector calculus that goes along with Maxwell's equations. You see a little bit of that in 3317, but 3318 is really the course where you really get the deepest understanding of Maxwell's equations and vector calculus. So here's some pictures kind of taken from 3318. So here's a slide where we're talking about transformer designs and how they work. Here's a slide where we're talking about eddy currents that flow inside the core of a transformer, and you can calculate those based on Faraday's law. Here's a slide, again, related to transformers, where we're now talking about power dissipation inside of a transformer core due to the nonlinear effect known as hysteresis, which a lot of iron cores have. Here's a slide where we're talking about how to calculate the fields of a high voltage power line over the earth using what's called image theory. Here's a slide where we're talking about the very basics of how an AC generator works. Here's a slide where we're talking about the very basics of how a DC motor works. And you get the idea. So it's a good foundational course where you learn the EM principles, that underlie all of the basic devices in power engineering, really, and all the fundamental principles that go along with those devices. 3318 is not a power engineering course. Now, you can take power engineering courses, obviously, but this is really a course that gives you the EM foundation for understanding everything that goes on in the power area. I mentioned that there's the optics course too, the optics and photonics, that you could take as one of your concentration electives. So optics, of course, is like an extreme case at very high frequency, where it's like light frequencies, even way above microwave frequencies, at the optical frequencies, where now people usually use specialized devices such as lenses or fiber optic guides, prisms, lasers as sources, and so on. Okay, and there's that course again, 5358, called Modern Optics and Photonics. So that could be one of your 7 concentration elective courses. All right, and again, it requires 3317 as a prerequisite, just like the microwave engineering and the antenna engineering courses did. Okay, let me also take a few minutes, if I could, to just plug a little bit graduate courses, and as I'll talk about in a second, what's called the AMP, the Accelerated Master's Program. Now, first of all, please be aware that as an undergraduate student, you are allowed to take graduate courses. The only thing you need is just permission of the instructor. And if you see a certain graduate course that you're interested in taking and you go and talk to that instructor, probably they'll give you permission. Usually they do. And so you can consider taking graduate EM courses if you're in the EM concentration area. If you're so inclined to do that, one course you might think of is called 6340. It's called Intermediate Electromagnetics. That's the official title. It's really the beginning graduate EM course. It's kind of like the counterpart of 3317, and it requires 3317 as a prerequisite. But think of it as 3317 at a little bit higher level. So it's like it's a first graduate course that's really related to EM, that covers the same kind of topics, a lot of the same topics as 3317, but at a higher level. But then some new topics too that you don't see in 3317, as you can see on this list here. So it's a very good course if you really want to get even more advanced EM than you would normally get as an undergraduate student. Another one, as I mentioned, is the 6353 RF and microwave electronics. And that one requires the microwave engineering course as a prerequisite. Okay. And as you can see from the list of topics, it goes into a lot of the active component design. So oscillators and amplifiers and so on, a lot of what we call the active microwave technology, not just the passive technology that you see in the microwave engineering course. Now, you probably have heard of this. It's on the undergraduate webpage. I invite you to read that if you want more details. But we have something called the Accelerated Master's Program here at UH and in our college. And it's a very good program for those of you that are thinking about the possibility of going into the master's program here in ECE after your bachelor's degree. Okay, if you go into the Accelerated Master's Program, you're not obligated at all to go to graduate school. But if you're even thinking about the possibility of going to graduate school and getting a master's degree, then I strongly encourage you to consider the Accelerated Master's Program. Okay, so what is the Accelerated Master's Program? Now, it's a program that allows you to double count, as it says here, up to 2 graduate courses. Graduate courses are 6,000 level courses. Okay, a 5,000 level course is still considered an undergraduate course, right? But it allows you to double count 2 graduate level courses for both your undergraduate degree and your master's degree. Okay. Now, the way it works is you can pick 2 6,000 level courses, any 2 that you want, and you can count them as your undergraduate electives to fulfill 2 undergraduate electives, but then you can also count them for your graduate master's program. So that saves you 6 hours in your master's program. So the normal master's program is a 30-hour program. So you get to shave off 6 hours of that by doing the Accelerated Master's Program. Now, here's a caveat, though. If you're interested in the Accelerated Master's Program, be aware that the college wants you to apply for the program and be accepted into the program before you go ahead and take your 2 graduate courses. Now, some students have gotten into trouble because they've gone ahead and they've taken 2 graduate courses, and then they applied for the AMP after they've taken one or even both of the graduate courses, and the dean doesn't really like that. And sometimes he allows it, sometimes he doesn't, but you're kind of rolling the dice. So to be safe, make sure you apply and be accepted in the program before you take the graduate courses. It's very easy to apply to the program. You just go to the undergraduate ECE webpage. You'll see a link to the AMP program. There's a form right there you can fill out and submit to Dr. Trombetta or to Amanda. And it's a very simple process, but make sure you do that before you take your graduate courses. Now, if you in the AMP program, again, it's 6,000 level courses that you have to take that get double counted, not 5,000 level courses. So be careful. So just as an example, let's say you wanted to take, let's say the microwave engineering course. The microwave engineering course as an undergraduate would normally be 5317, okay? But if you take 5317, you cannot count that also in your graduate program. So you must take the graduate version of the microwave engineering course, which is called 6351. That can be used to be double counted both for your undergraduate program and your graduate program, your master's program. Okay, so be careful about that point. Okay, so I think that's the last slide. So let me start answering questions if I could. So I see some people are chatting here. Let me go to the chat here.
I believe some of the questions were for a previous talk.
Oh, okay, that's okay. That's fine. Thanks. Okay.
But do you guys have any questions about the applied electromagnetics concentration? Okay. Well, if I could ask you, so from my understanding, more students in the applied EM concentration tend to do undergraduate research, at least compared to other concentrations. Could you give us some, could you talk about some of the research opportunities within this concentration?
Yeah, well, yeah, to be honest, I'm not aware if there's more of them in the EM area or not that are doing undergraduate research. That's interesting to hear. I haven't heard that before, but that's interesting to hear. But anyway, yeah, well, one of the nice things about UH is that we have some programs for undergraduate research, and the university really encourages undergraduate research. So you may have heard these programs called SURF and PERS. So PERS is PURS. I forget what it stands for. But anyway, the PERS program is the program that gets undergraduate students involved in research during the fall and spring semesters. And the SURF program is like the counterpart for the summer semesters. Now, what you can do is there's deadlines. I think usually Dr. Long sends out like from the Honors College a notice about this, and there's some kind of deadline to apply for the SURF and PERS program. But they're really good programs, and if you apply for them and you get selected, then you'll get to actually do research with an advisor. And I think the program even pays you something too. It's not much, but pays you a little stipend too. So you get actually paid to do your undergraduate research too. So that's probably the nicest way to do research as an undergraduate. Now, you don't have to be in PERS or SURF. I mean, if any student is welcome to just go to a faculty member and say, hey, I'm interested in doing undergraduate research. Do you have anything for me? And just, begin a dialogue with a faculty member. And you can just kind of informally hook up with a faculty member like that who might have something that they could, get you involved with, maybe get you into the lab and get you on some kind of a project. But again, the SURF and the PERS programs are a more formal way of doing it. And it's really a nice way to do it because then you get official recognition. You can put that on your resume that you were a SURF or a PERS student, and it even pays you something too. So I'd really strongly encourage you to consider that.
Got it. Thank you. I appreciate it. And then briefly, you mentioned earlier that you can take graduate level courses if you get permission from the professor. Is that only within the College of Engineering, or could that apply to courses outside of the college, say in the Department of Mathematics, to take a graduate math course?
You'd have to check with them because, see, every college and really even every department sets their own rules. So I know in our department, if you go talk to an instructor and they give you permission, then you can enroll. Okay. Now you have to do some kind of, paperwork. So after the instructor gives you permission, you may have to go see either Amanda or maybe Kelly, who's like Amanda's counterpart at the graduate level, and one of them will actually put you in the course. Okay, but it's a pretty simple process. But in terms of permissions, all you need is just to go talk to the instructor and get permission. Other departments, it's up to them, right? They may have the same kind of policy, they may have a different policy. It's really up to them.
Got it. Thank you. Let's see. I know you said you were interested in maybe applied EM. Do you have any?
Yeah. So I was here.
Oh, no, I got it. Let me see. We have a student who's interested in this concentration, so he'll be asking you a question.
Yes. So I am interested in going into RF engineering, and I was wondering, does that correlate over, or being in this concentration, will that carry over into maybe a graduate program?
Yeah. And so remember, for you, two really important courses would be the microwave engineering course, which of course is required in the EM concentration area, but then also consider maybe this graduate course right here. This is the one that's kind of right up your alley if you want to go into RF engineering.
Yes. And does this course also apply to that accelerated master's program?
Yeah, any two graduate courses can be used for the AMP, any two.
Okay. I just wanted clarification on that. Thank you.
Yeah, so this could be an excellent one to consider if you want to do the AMP. Absolutely.
Yes, I see that. All right. Okay. Thank you.
All right. I guess if I have another quick question. So so I know at least within the power concentration, most students end up going into power, and there's similar situations for other concentrations. Within this concentration, where would you say most of your students end up working at? Because I know you said there was a lot of demand for people looking for microwave engineers and antenna engineers, obviously. But could you let us know where specifically this demand lies?
Yeah, now I'm a little bit, more familiar with it answering that question sort of for graduate students, because I work with them most often because, I'm the director of graduate studies in our department. Maybe Dr. Trombetta could answer more for undergraduate students, but let me just say, based on my experience, though, a lot of them end up going with, large kind of wireless companies or aerospace type of companies. Another place where they end up going is like geophysical type of companies, because they do a lot of what's called well logging, which is basically using EM to do subsurface sensing. Okay, and then some of our students have gone to in the medical industry, because in the medical industry, they're doing a lot of research that relates to EM. For example, some of the research involves what happens when you put implantable devices in the human body, and then the patient goes to an MRI machine, for example, and you design devices like pacemakers or any kind of device that go into the body. You need to do a thorough EM study to see what the specific absorption rate is, how the body's going to heat up, and so on. So a lot of our students are interested in that kind of field. And in fact, a lot of our graduate students, in fact, are doing research in that kind of field. So that's a good area too. So, but aerospace and wireless are probably two of the really big ones, in my opinion.
You got it. Thank you. Let's see. Do you have any questions? Let's see. Let me check the chat. Okay. So someone just asked, have any of your students launched a CubeSat?
Well, yeah. So that was a senior design project. It started out as a senior design project, and then it turned into a bigger project. But I showed you that picture. That was an antenna that they actually built for the CubeSat. Now, we ourselves did not launch it, but that was a project that ended up getting sponsored by NASA. And so we're working in collaboration with NASA to go ahead and actually design it for the CubeSat. And then more recently, this was just a few years ago. Now, this was a PhD student, but he was working with me to design another type of antenna that was going to go on a CubeSat that got launched by NASA. The CubeSat was called Kenobi, and it was on a mission that was launched from the ISS. And its mission was to go out from the IS and kind of scan around and take pictures and transmit data back. So they wanted just near field communications, and they thought a microstrip antenna on the CubeSat would be a good fit. So we designed a microstrip antenna for him to do that. That was a few years ago.
It's nice. It's really cool. For those of us who don't know, when you say CubeSat, what do you mean?
Oh, sorry. So CubeSat is, you can Google it. I'm sure Wikipedia has a page on it. They're just small, literally handheld satellites. They could be cube shaped. That's called a 1U CubeSat, 10 centimeters by 10 centimeters by 10 centimeters. But then you can have like 2U and 3U is like three of them, cascaded together. And it's kind of a modern trend nowadays to try to do as much as you can with CubeSats rather than these big, full-blown, really expensive satellites. And NASA, for example, is really interested in doing more and more with CubeSats. CubeSats are relatively cheap. I mean, everything's relative. I mean, maybe one costs, $5,000 or something, but that's nothing for NASA. But a big satellite costs many millions of dollars. Okay, so if you can do a similar job as a big satellite with, let's say, a constellation of small CubeSats, that's going to be extremely cost effective. And not only that, but because CubeSats are so small, it opens up the opportunity for a lot of people to get involved. Even students, like I was saying, can get involved in designing and building CubeSats. You're not going to have a student team designing a $40 million satellite, right? But they can get involved with CubeSats. And so it opens up the opportunity for students, for small companies, for a lot of people that couldn't otherwise have get involved in the satellite industry.